This video reviews temperature and volume relationships. The gas law that is all about temperature and volume relationships is Charles's law. Around 1800, Jacques Charles discovered that gas volume and absolute temperature are directly proportional at constant pressure. Remember that absolute temperature means that temperature must be expressed in Kelvin, and directly proportional is a positive graph like this. So for example, if the absolute temperature expressed in Kelvin is doubled, the volume is doubled. If the volume is cut in half, the absolute temperature is also cut in half. You could also say that if the volume is quadrupled, so is the temperature, etc. Here's our equation. What this means is that when gas pressure is held constant, the following equation expresses the volume and temperature relationship. Volume is right here, so volume 1 over temperature 1 expressed in Kelvin equals volume 2 over temperature 2. You could also say volume initial and volume final if you wanted to. Notice that this equation looks very, very similar to our temperature and pressure equation that we worked on last week. The point is that if any three of the variables in this equation are known, then the unknown fourth variable can be calculated. And that's what we're going to do today. So here's our first example. This is the easy one where we simply plug in the values. So our volume can be expressed in any metric unit of volume, liters or milliliters. That's fine, but our temperature must be in Kelvin. So we're going to go ahead and start by plugging in our variables here. So we have 100 liters over 100 Kelvin equals, we don't know volume 2, and we have temperature 2 as 200 Kelvin. There's two ways to solve this. We can cross multiply and then divide to find volume 2. We can also just look to see the relationship between volume 1 and temperature 1 and what we know about our second set of information. We should hopefully be able to see here that we have our first temperature as 100 and our second temperature as 200, and then 100 times 2 equals 200. Remember, this is a direct relationship, so that means that initial and final values are going to change by the same factor. So to find our volume 2, we can simply multiply times 2. So V2 is going to equal 200 liters. But if you don't believe me, we can cross multiply and divide to find our answer. So let's do that real quick. 100 liters times 200 Kelvin equals 100 Kelvin times volume 2, which is the one we don't know. We want volume 2 to be by itself, so we have to divide by what's stuck to it because the 100K is stuck to it by multiplication. So we do the opposite. That cancels. We divide by the same thing on both sides. Our units of Kelvin cancel. We have 100 and 100 on the top and the bottom, so we can cross those out. We're left with 200. And our units that we're left with are liters. So notice that we get the same answer, 200 liters. There we go. Here's our second example. This says at 273 Kelvin, the volume of a sample of nitrogen is 30 liters. What will the temperature be if the volume increases to 300 liters? Okay, so we want to pull our information out of this equation. So at 273 K, so the K stands for Kelvin, so this is temperature 1. The volume of a sample of nitrogen is 30 liters. Okay, this is V1 because liters is volume, and the sentence tells us volume. What will the temperature be? Okay, so that means we don't know T2. T2 is our question mark. If the volume increases to 300 liters, so 300 liters is our V2. And then we plug these into our equation. So 30 liters over 273 Kelvin equals 300 liters over T2, which is the part we don't know. Okay, so we can solve this two ways again. We can cross multiply and divide. We can go ahead and do that first. So 30 liters times T2 equals 273K times 300 liters. We want the temperature by itself, so we have to divide by 30 liters on both sides to undo this multiplication that's on the left side. All right. So now liters are going to cancel. And 300 divided by 30 is 10, so we could cancel the 30 here and replace it with 10. And all this stuff on the left side cancels. So now we have T2 equals 273 Kelvin times 10. 273 times 10, we just add a 0 on the right side of the 273, so that gives us T2 equals 2,730 Kelvin. That's our answer. And then the fast way to do this would be to look at the factor in between 30 liters times what equals 300 liters. It's times 10. 30 times 10 equals 300. So we're going to multiply by 10 on the bottom too, and that'll give us the same answer that we got. That gives us the 2,730 Kelvin. So either way works. You only have to do one way, but either way works. Here's example 3. At 500 Kelvin, a 1,000 milliliter sample is at standard pressure. If the pressure is held constant and the temperature decreases to 5K, 5 Kelvin, what is the new volume in milliliters? All right, so we're going to find all of our information. So at 500 Kelvin, K stands for Kelvin, that is always temperature, so here's temperature 1. A 1,000 milliliter sample. Milliliters is volume, V1. It's at standard pressure if the pressure is held constant. So this is telling us that we know something about pressure, but thankfully we know that it's held constant. That allows us to use Charles's law. If we didn't have pressure constant, we couldn't use this equation. So that's good. The temperature decreases to 5 Kelvin. So this is T2. What is the new volume? That's what we don't know. Great. So 1,000 milliliters over 500 K or Kelvin equals, we don't know, V2 over 5 Kelvin. Okay, so this is one of those where I think it's pretty clear that we can find the factor that goes between 500 to 5. 500 to 5, in other words, 500 divided by what equals 5? 500 divided by 100 equals 5. You can check your work by doing 5 times 100. That's 500. So here we have, it's a factor of 100. So we can divide by, oops, not 1,000, 100. On both sides, or on the top and the bottom, and we're going to get, well, 1,000 divided by 100 is 10. So our V2 equals 10 milliliters. You could have also cross-multiplied and then divided this one. You would have done 1,000 milliliters times 5 Kelvin. Then you would divide it by 500 Kelvin. You get the same thing, because that would be 5,000 divided by 500. That still equals 10. Thank you for watching.